Preparing for a Reactor Operations Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain reactor criticality, and why is it central to reactor operations? Criticality means the neutron population is steady from one generation to the next, so reactor power is stable. If the reactor is subcritical, power decreases. If supercritical, power increases. In operations, I care about controlled reactivity changes because delayed neutrons give operators time to respond safely. I would always tie criticality to procedure compliance, verified indications, conservative decision-making, and awareness of factors like control rods, boron concentration, temperature feedback, and xenon behavior. While answering, focus on neutron balance, subcritical, critical, and supercritical states, delayed neutrons, reactivity control, and why operators must maintain predictable, procedurally controlled changes in reactor power. Question 2. What actions would you take if reactor power began rising unexpectedly? An unexpected power rise is treated as a safety-significant condition, not as something to troubleshoot casually. I would verify key indications, announce the condition clearly, enter the appropriate abnormal operating procedure, and support the senior operator or shift manager. If parameters approach trip criteria, I would not hesitate to support a reactor trip. The priority is maintaining the plant within analyzed limits, protecting the core, and preserving barriers, while avoiding unapproved actions or assumptions. Make sure to cover immediate safety mindset, verification of indications, procedure use, communication with the control room team, automatic protection systems, manual trip criteria, and conservative escalation. Question 3. How do temperature coefficients affect reactor stability during operation? Temperature coefficients describe how reactivity changes as fuel or moderator temperature changes. A negative coefficient is stabilizing. As temperature rises, reactivity decreases, which helps oppose power increases. Fuel temperature feedback is fast, while moderator effects depend on reactor design and conditions. I would emphasize that these are engineered safety characteristics, not operator substitutes. Operators still monitor power, temperature, pressure, flow, and margins continuously, because stability must be confirmed through instruments and procedures. In your answer, talk about negative temperature feedback, moderator and fuel temperature coefficients, power stability, thermal margins, and how these effects support but never replace operator monitoring. Question 4. Explain xenon poisoning and how it affects reactor power maneuvers. Xenon-135 is a strong neutron absorber produced from iodine decay and directly from fission. After a power reduction or shutdown, xenon can build up and suppress reactivity, which may limit restart or power ascension timing. During power maneuvers, I would expect reactor engineering and operations to account for xenon transients in the plan. The practical point is simple. Power changes are not just mechanical actions, they are nuclear physics changes managed through approved procedures. Be sure to mention iodine decay, Xenon-135 neutron absorption, post-shutdown xenon buildup, power maneuver constraints, operator planning, and coordination with procedures and reactor engineering. Question 5. What is your understanding of ALARA, and how would you apply it on shift? ALARA means keeping radiation exposure as low as reasonably achievable, not merely below limits. On shift, I would apply it through strong work planning. Minimize time in dose areas, maximize distance, use shielding, follow radiological work permits, and respect dose alarms. I would also challenge unnecessary entries and support pre-job briefs that identify dose hotspots. Good ALARA behavior is operational discipline. It protects people while maintaining safe, reliable plant performance. While answering, cover time, distance, shielding, dose planning, radiological work permits, contamination control, pre-job briefs, stop work authority, and balancing production goals with personnel safety. Question 6. How would you handle conflicting indications between two reactor instruments? Conflicting indications require validation, not guessing. I would compare the instruments against related plant parameters, check alarms, review known equipment status, and involve the control room team. If one indication affects safety limits or technical specifications, I would take the conservative position until proven otherwise. The key is to follow abnormal procedures and use multiple independent signals where available. Instrument problems can become operational problems if the team normalizes uncertainty or delays escalation. Make sure to cover instrument validation, comparison with related parameters, conservative assumptions, procedure guidance, equipment status tracking, communication, and avoiding single indication decision-making when safety is involved. Question 7. What are technical specifications, and why are they important to reactor operations? Technical specifications are legally binding operating requirements that define safety limits, limiting conditions for operation, surveillance requirements, and required actions. They translate the plant safety analysis into operational boundaries. If equipment becomes inoperable, tech specs tell the crew what actions and completion times apply. I would treat them as a primary decision tool, especially during equipment failures or mode changes. Strong operators do not rely on memory. They verify applicability and document compliance carefully. In your answer, include limiting conditions for operation, surveillance requirements, action statements, regulatory basis, operability decisions, compliance timelines, and how operators use them during abnormal conditions. Question 8. Describe how you would prepare for a reactor startup or power ascension. A reactor startup or power ascension starts long before control rod motion or power change. I would review the approved procedure, prerequisites, equipment lineup, plant conditions, reactivity plan, and required surveillance status. The crew briefing should cover expected responses, hold points, communications, contingencies, and roles. During execution, I would use strict placekeeping and independent verification. The goal is a controlled, predictable evolution where every change is anticipated, monitored, and reversible within procedure limits. Be sure to mention procedure review, prerequisites, equipment lineup, reactivity management, hold points, briefings, independent verification, communication standards, and readiness of protection and cooling systems. Question 9. What would you do during a reactor trip or scram? During a reactor trip, the first priority is to verify the reactor is shut down and that safety systems actuated as expected. I would check critical parameters, neutron flux, rod position, reactor coolant pressure, temperature, level, flow, decay heat removal, and electrical supply status. Then I would support entry into the emergency or abnormal operating procedure. A trip is not over when power is zero. The plant must be stabilized, cooled, and kept within safety limits. While answering, focus on immediate verification of shutdown, automatic safety system response, core cooling, heat removal, electrical status, procedure entry, crew communication, and post-trip stabilization. Question 10. How do you maintain situational awareness during high-workload control room conditions? In high-workload conditions, situational awareness depends on structure. I would prioritize safety functions first: reactivity control, core cooling, heat sink, containment, and electrical power. I would use three-way communication, clear role assignments, procedure placekeeping, and periodic status updates. Alarms should be interpreted in patterns, not as isolated noise. If the team is losing the picture, the right move is to pause non-essential actions, rebrief, and restore command and control. Make sure to cover prioritization, three-way communication, command and control, alarm management, procedure adherence, cross-checking, task delegation, and recognizing when to slow down or stop. Question 11. What is the difference between an abnormal operating procedure and an emergency operating procedure? Abnormal operating procedures generally address off-normal plant conditions before they become emergencies, while emergency operating procedures protect critical safety functions after major transients or accidents. Many AOPs are event-oriented. EOPs are often symptom-based, focusing on reactor shutdown, core cooling, heat removal, and containment. Correct procedure entry matters because it aligns the crew with analyzed response strategies. I would avoid freelancing and ensure transitions between procedures are deliberate, announced, and documented. In your answer, explain event severity, symptom-based versus event-based guidance, entry conditions, safety function protection, operator priorities, and why correct procedure selection matters. Question 12. How would you respond if a safety-related pump failed during operation? A safety-related pump failure requires quick assessment of plant impact and required actions. I would verify the failure, check whether redundant trains are available, review alarms and supporting systems, and determine operability with the licensed crew and engineering support. Technical specifications may require action statements or mode changes depending on the system and condition. I would also ensure maintenance is engaged, but operations owns the immediate safety response and plant configuration control. Be sure to mention immediate assessment, redundancy, operability, alarms, tech spec implications, alternate trains, procedure entry, maintenance coordination, and conservative communication with supervision. Question 13. How do chemistry controls support safe reactor operation? Chemistry control protects both reactivity management and equipment health. In some reactor types, boron concentration directly affects reactivity, while pH, conductivity, oxygen, hydrogen, and impurities influence corrosion and material degradation. Chemistry trends can also indicate fuel integrity issues or system leakage. As an operations engineer, I would treat chemistry data as operational information, not a separate department's paperwork. Good coordination with chemistry helps preserve barriers, extend component life, and avoid surprises during power changes. While answering, cover corrosion control, boron or reactivity chemistry where applicable, dissolved gases, conductivity, pH, radionuclide monitoring, fuel integrity indications, and coordination between operations and chemistry teams. Question 14. Tell me about a time you would use conservative decision-making in reactor operations. Conservative decision-making means choosing the safe, procedurally supported path when information is incomplete or plant conditions are uncertain. For example, if an indication challenged an operating limit but had not yet been fully validated, I would preserve margin, notify the shift manager, and enter the applicable procedure instead of waiting for perfect confirmation. The mindset is not fear, it is respect for defense in depth. Once stable, the team can troubleshoot methodically and document the basis. Make sure to structure the answer around uncertainty, safety margin, procedure compliance, stop work authority, escalation, communication, documentation, and learning mindset, rather than appearing risk-averse without reason. Question 15. What human performance tools are most important in reactor operations? The most important human performance tools are the ones that prevent small mistakes from becoming plant events. I rely on self-checking, three-way communication, peer checks, independent verification, procedure placekeeping, and pre-job briefs. A questioning attitude is especially important during routine evolutions because familiarity can lower standards. These tools may look simple, but they create barriers against wrong component manipulation, missed steps, and miscommunication. In reactor operations, disciplined basics are a major safety system. In your answer, discuss three-way communication, peer checks, independent verification, procedure use and adherence, pre-job briefs, questioning attitude, placekeeping, self-checking, and error traps during routine tasks. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.